Welcome to Physical Chemistry, VLE modeling for an ethanol water mixture at 25 degrees Celsius. We will determine activity coefficients from VLE data, fit Wilson, NRTL, and UNIQUAC models, and compare the average absolute relative deviation, or AARD, chemically, mathematically, statistically, and graphically. The core vapor-liquid equilibrium relation for a binary at fixed temperature is Raoult with activity coefficients. For each component I, y sub I times p equals x sub I times gamma sub I times p sat sub I. Solving for gamma sub I gives gamma sub I equals y sub ip divided by x sub I p sat sub I. We can compute p saturation at 25 degrees Celsius using Antoine equations in consistent units. Here is a compact, clean data table for ethanol in the liquid mole fraction, ethanol in the vapor mole fraction, the total pressure in millimeters of mercury, and the activity coefficients implied by the vapor-liquid equilibrium relation. Nothing overlaps. Each entry has its own clear cell. Next, the three local composition models. First, Wilson with parameters lambda 1, 2, and lambda 2, 1. Second, NRTL with interaction parameters tau 1, 2, tau 2, 1, and the non-randomness alpha. Third, UNIQUAC with size and surface parameters R and Q, and interaction a 1, 2, and a 2, 1. We will fit these parameters to minimize the average absolute relative deviation of activity coefficients. Now, we search for parameters that minimize average absolute relative deviation on the activity coefficients. We will use a quick course grid to keep computation light, but reliable for teaching. Here is the graphical comparison. Activity coefficient of ethanol and of water versus liquid mole fraction of ethanol. We show experimental points and the three model curves. Statistically, the average absolute relative deviation summarizes fit quality across both components. Here are the numbers we obtained. Wilson AA, our D equals 11.42%. NRTL AARD equal 9.30 pers. UNIQUAC our D equals 11.78%. Chemically, local composition models capture the strong ethanol-water non-ideality with activity coefficients greater than 1. Mathematically, each model translates molecular asymmetry into excess Gibbs energy and therefore activity coefficients. Graphically, you can see which curve follows the experimental points most closely across composition. Takeaways. 1. Compute activity coefficients directly from vapor-liquid equilibrium data using the measured vapor fraction, the total pressure, and saturation pressures. 2. Fit Wilson, NRTL, or UNIQ, UAC parameters to minimize average absolute relative deviation. 3. Always compare models chemically, mathematically, statistically, and graphically to ensure the model you choose is robust for your process design.